My name is Maliborski, and I would like to present the results of a recent study of radical regulatory properties of radiosensitizers based on 1,2,4-triazole and imidazole. It is known that interaction of reacting oxygen species with bioorganic compounds leads, as a rule, to the formation of carbon-centered radicals from the starting molecule, either by hydrogen atom abstraction or addition to the double bond. Further formation of carbon-centered radicals depend on the respective structures. The radical volcule types are consumed mainly in reaction with oxygen, forming oxidation products, as is shown on scheme 1, which corresponds to lipid peroxidation. If the structure of organic molecule contains two functional groups, the realization of a fragmentation process is possible, as shown on the scheme below, which corresponds to the free radical lipid fragmentation process. The ratio between fragmentation and oxidation depends on oxygen concentration. In our work, we use radiolysis of substances as ethanol as a convenient model for studying the reactivity with respect to alpha-hydroxylated carbon and oxygen-centered radicals, correspond to the main types of organic radicals formed during hypoxia. This was used to identify the radical regulatory properties of nitroderivatives of imidazole and triazole. Obtained data will help us optimize the use of radiation sensitizers in a complex therapy of radio-resistant tumors. So, wherefore, a series of nitrogen heterocycles, mainly nitroderivatives of imidazole and triazole, were synthesized, and the interaction with carbon and oxygen-centered radicals were studied by steady-state radiolysis of the ethanol solutions. The structures of the compounds are mentioned on the slide, and you can see the arrays of triazole-based substances and imidazole-based. So then I would like to give a short description of a model we used. During ethanol radiolysis, the alpha-hydroxyethyl radicals are formed. In the absence of the additives and oxygen, alpha-hydroxyethyl radicals are consumed with approximately the same probability in bimolecular radical recombination as disproportionation reactions, with the formation of butanediol 2,3 and acetaldehyde, respectively. In the presence of oxygen, carbon-centered radicals are consumed, and in the reaction with oxygen and peroxy-hydroxyethyl radicals are formed, which are subsequently transformed into the hydrogen peroxide and acetaldehyde, which is mentioned on the schemes in the bottom corner of the slide. So the results of the experiments from the substances 1 to 9 in the pure ethanol are mentioned on the slide. As you can see, the experimental data suggests that all 1,2,4-triazole derivatives from 1 to 9 show themselves as oxidizing agents, changing the ratio of yields of generated ethanol radiolysis products in the favor of acetaldehyde. It has been established that 1,2,4-triazole only slightly changes the ratio of radiation chemical yields, while its nitro and denitro derivatives quantitatively oxidize alpha-hydroxyethyl radicals, which is present as the absence of butanediol on the interaction species. It also should be mentioned that the yields of degradation of the compounds in the study were less than 1 molecule per 100 electron volt, which is typical for substances that integrate with several alpha-hydroxyethyl radicals and or undergo regeneration to the parent structures. So on the next slide, oxidative properties of nitroimidazole derivatives were tested, also using steady-state gamma radiolysis of the rated 1 molar ethanol solutions in water. As you can see, substances from 10 to 15 shown a significant increase in yields of acetaldehyde. So you can see in case of substances 13 and 14, the presence of nitro group shows an increase in the oxidative ability of the tested compound, and the absence of the butanediol in the tested system is observed. So therefore can be stated that the addition of nitro group to the azole cycle significantly increases the oxidative ability towards carbon-centered radicals. The ability for derivatives of 1,2,4-triazole to interact with oxygen-centered radicals was tested using the steady-state gamma radiolysis of ethanol solutions saturated with oxygen. The experimental conditions are mentioned on the slide. The addition of nitro derivatives resulted in insignificant decrease of radiation chemical yields of acetaldehyde and hydrogen peroxide, which means the substances have no reactivity towards oxygen-centered radicals formed in the tested system. This could be confirmed by negligible low additive decomposition rate. As for derivative of imidazole, results are shown on the slide, and therefore it can be stated that nitro derivatives of triazole and imidazole do not interact with oxygen-centered radicals. As conclusion, the results obtained in the study are important for understanding the molecular mechanism of the formation of radiation damage during radiation therapy of cancer diseases using radiation sensitizers based on nitro derivatives of triazole and imidazole. These compounds can be used as radiosensitizers for hypoxic solid tumors. The most notable examples of such compounds are sanazole and metronidazole, which are used as reference compounds in the current study. Hypoxic tumors have a reduced partial pressure of oxygen. Hence, they have a low radiological sensitivity to ionizing radiation. The ability of all nitro derivative of imidazole and triazole to quantitably oxidize carbon-centered radicals in hypoxic condition, and at the same time low reactivity towards oxygen-centered radicals formed during radiolysis make investigated substances potent to increase the effectiveness of radiotherapy of hypoxic tumors with normal oxygenated cells will be unaffected in such process. So thank you for your attention. Are there any questions?
Thank you to the speaker. Any questions?
Yes, please. Can I again?
Yes,
of course.
I like to ask. All of these presentations are great with many results. So I congratulate. Really, I have to ask something always. This is very interesting presentation and many results. I would say I couldn't realize why you tested diazoles and triazoles. Why these compounds were so interesting?
The derivatives of imidazole cycles or triazole cycles possess many biological properties like antiviral, cytotoxic activity, and addition of the nitro groups makes important as radiation sensitizers. So the metronidazole is used in clinical practice as a radiosensitizer. So we would like to make the assay of these compounds can be less toxic than metronidazole or more effective. As it was shown, as we tested the nitro derivatives of histidine, we tried to make the radiosensitizers with potent biological activity and selectivity, because the tumors are growing fast and they need a lot of building material for their growth.
And if you compare monoazoles, diazoles, and triazoles, is there some differences in this? Could you compare them, or you have many results so you couldn't compare that?
We have not many results of monoazoles. As for
and DN3?
At DN3, the experiment conditions were made so that we tested them in water ethanol solution for diazoles and in pure ethanol for triazoles. It is because of the solubility problems we have, as we try to test the derivatives of the existing amino acids, and histidine is pure or poorly soluble in ethanol and pure ethanol. So there will be a mistake to make such a comparison in front.
Mm-hmm. So ethanol could be a problem. Huh? Okay, thank you very much.
Okay, I have one more question. Your part of work was connected only with testing of these compounds, or also with chemical synthesis of these compounds?
Yes, we did the synthesis part of these compounds, but we mainly will focus on testing them. So what questions have you have about the synthesis?
Okay, understand. Great. Thank you.